Come, myself Giridhar Jain, Assistant Professor in Electronics and Telecommunication Engineering, Walchand Institute of Technology, Solapur. Today I am going to deliver a lecture on Pass Transistor Logic Part 2. Learning outcomes. At the end of this session, students will be able to elaborate solution for issues in Pass Transistor Logic. Contents of the session are level restorer, multiple threshold voltage transistors, transmission gates, multiplexers using transmission gate and layout. For a pass transistor logic, the main problem is that the full voltage swing at the output of this NMOS is not available, and therefore there is a static power dissipation across the pass transistors. Now to overcome this problem, so here a level restorer transistor MR is connected as shown in figure. So this is the input, so this is the NMOS, then this is the internal capacitance, this is a CMOS inverter, and this is output. Now output, that out as shown in figure, so it is connected to gate of the PMOS, and this PMOS will act as a restorer. This is MR, and this point goes to the X. Now how the circuit works? Now if input A is equal to 0 and B changes from 0 to 1, so when this switch, that Mn will become on, so this 0 passes through this NMOS and X is equal to 0. If X is equal to 0, which is stored by this internal capacitance, and the output of CMOS inverter is logic 1, and this goes to gate of PMOS, and therefore this PMOS is off and this 0 will retain as it is. So there is right. And now let us check for the another condition. Now if A is equal to 1 and B changes from 0 to 1, so what happens? The output of this first NMOS will become 1, and that 1 is inverted by the CMOS inverter and it will become 0. Now as soon as the output becomes 0, that goes to gate of PMOS, so this PMOS will conduct, and whatever the degradation is taking place at the voltage X, so that is overcome by this restorer, because output is 0, so this PMOS becomes 1, and this 1 which was less than VDD, so that is restored to VDD, because there is a low impedance path from VDD to the node X, right? So this is the first solution to reduce the static power dissipation. So this is a restorer. Now for this circuit, the full swing on the node X is available due to restorer, hence no static power consumption by the inverter. So no static backward current path through the level restorer and the pass transistor, since restorer is only active when A is high. Now for the correct operation of this circuit, the MR must be sized correctly. So sizing of the MR is important. Now let us understand the sizing of the MR, how it affects the circuit performance. So here, if you go back to earlier slide, so this is the MN, this is the M1, M2, and this is the MR, that is a restorer. So size of the W by L2, W by L1, and W by Ln, so that is given, and we are changing only the W by LR. So this is W by LR is 1 divided by 0.25, So this is the voltage, that is the output, right? So this is the voltage versus the time. Now if W by LR is increased, so this is the response. If we increase that from 1.25 to 1.5, this is the response, that is somewhat better. And if you make W by LR 1.75 divided by 0.25 micron, so you will get the better performance, and the node X never goes below the Vm. So that Vm is the threshold voltage of that inverter, Vx of the inverter, and therefore the output never switches. So this is the desired. So you have to design the sizing of that MR properly so that the required performance is achieved, and that is elaborated in this slide. So restorer has speed and the power impact. So it increases the capacitance at X, slowing down the gate, increases TR but decreases TF. Now solution number 2 is using the multiple VT transistors as shown in the figure. So this is CMOS inverter 1, this is CMOS inverter 2. Now these two MOSFETs are low VT transistors, right? Now this is on and this is off, but having the leakage problem. So due to this, what is happening, as this is a leaky, so when the input 2 is 0 and input 1 is 2.5, here VDD is taken as 2.5. So one input, this is 1 and this is a 0. So this PMOS is conducting, this NMOS is conducting. Now this device is on and this is a leaky, and therefore you will find that there is a short circuit from that supply to the ground as shown in figure. So that we call as a snake path, right? So impact static power consumption due to the sub-threshold currents, the pass transistors, so even if VGG is below VT. Now third solution is the transmission gate. Now transmission gate is nothing but the parallel connection of PMOS and NMOS as shown in figure, and this is the symbol of the transmission gate. Now in this figure, the A is equal to B if C is equal to 1, right? So here that A is equal to logic 1, so that 1 will be passed through PMOS, and in second figure that A is equal to 0. So here you can see if A is equal to 1, so it will be passed through PMOS, because the PMOS passes good 1 and the NMOS passes good 0. So full swing bidirectional switch controlled by the gate signal C, A is equal to B if C is equal to 1. Now resistance of the transmission gate. So here PMOS and NMOS are in parallel. Let the resistance of PMOS is RP and NMOS is RN. So as the input here it is a 2.5 and output is changing, whenever V out is changing, how the resistance of the PMOS and NMOS is varying, that is RP and RN as shown in figure, and the R equivalent is the parallel combination of RP and RN. So this is R equivalent. So this R equivalent is approximately constant. Okay. Now pause this video and think on the following question. So how to design multiplexers using pass transistor logic? Now pass transistor logic, we are using transmission gate. Now this is one transmission gate and this is a second transmission gate. Now for the lower transmission gate, the input is S, and here this is a S bar. Now here it is a S, and this is a CMOS inverter. Now whenever S is equal to 0, the upper transmission gate is conducting, and therefore output is in 2, and the expression for output, so here F is given by here complement of here in 1 into S, and into here it is a S bar, right? And on the right hand side you can see the layout of this 2 as 1 mux. So here you can see this is a P diffusion, so here 2 PMOS, here N diffusion, this is a polysilicon, so here there are 2 NMOS, and here one transmission gate, this is another transmission gate. Now input is in 1, in 2, this is S minus S, this is also S and minus S, this is VDD, and this is a ground. Now the this square which are in black color, so these are the contacts, okay. So here N well is not shown in this layout, so N well should be drawn for fabrication of the PMOS, that is here, so you can draw the N well, okay. Now these are references. Thank you for watching the video.